Now we want to look at related rate problems. Related rates are situations where you have one or more pieces of a situation that can change and or that are changing, and you know how fast one thing is changing and it's causing something else to change, and you want to figure out how fast that other thing is changing. There's all sorts of situations here, and I'm going to go through a bunch of different examples over the next few videos. We'll start with this one. The idea here is we have a drop of water that falls into a still pond, and a circular ripple moves outward from that point. The circle getting bigger and bigger as it spreads here. And I'm told that the circular ripple expands in a way that its radius is increasing at a constant speed of 6 inches per second. So if I let r equal the rate, see if I can spell radius of the circle, then the 6 inches per second is the rate at which the radius is changing. This is a dr dt. Notice the radius of the circle, we're going to measure it in inches. So inches per second is change in inches divided by change in seconds, change in radius divided by change in time, right? So they tell me dr dt is 6 inches per second. The question is, how fast is the area changing when the radius is 15 inches? So they asked me the question of the rate of change in the area, right? Notice both the radius and the area are functions of time. That is, as this ripple grows and moves, the radius is getting bigger, the area of the circle is getting bigger. And so they're both functions of time, and I'm asking information about how they're changing, so I'm asking information about how those functions, what's the derivative of those functions, right? dA dt is equal to what when r equals 6? No, when r is 15, sorry. I was looking at the wrong number. I was looking at that one, when r is 15 inches. Now, related rate problems are all very similar in the sense that they tell you about one rate, they ask you about another rate. They might give you a particular instant in time when you're interested in this. The setup is a little different each time because are you talking about a circular ripple? Are you talking about a sliding ladder? Are you talking about a snowflake falling? I mean, there's all sorts of different setups, situations. But the idea, the process is the same. Identify the rate that's given, right? In terms of, draw a picture, and in terms of variables of this picture, I have the radius, I have an area. They tell me dr dt. They ask for dA dt. What I need to do now is find a relationship between r and a that's always true. And, in this case, I happen to know that the area of a circle is pi times the radius squared. Whether the radius is big or whether the radius is small, the area is pi times the radius squared. Okay. Now, I'm thinking of this as functions of time. The area is a function of time, and the radius is a function of time. But they're equal to each other. This function is always equal to that function because the area of the circle is always pi times the radius squared. So the thing is, if these two functions are equal to each other, then I can implicitly differentiate with respect to time and end up with an equation that relates the rates. I start with an equation that relates the variables without derivatives, and then I'm going to be able to find an equation that relates the rates. So dA dt here is the derivative of pi r squared. Now, r is some function of t, so we got a chain rule going on here that I've got pi times 2r, that would be the derivative with respect to r, but then multiplied by dr dt. Okay. Now that I have done this, implicitly differentiated, I have an equation now that relates the rate of change in a with the rate of change in r. So started with a relationship between A and R. Now I have a relationship between the rates. I have related the rates, right? That's why it's called a related rate problem. Now that I've done that, I can plug in everything I know and solve for the one I don't know. dA dt is the thing I'm looking for. 2 pi times r, well, they're telling me that I'm interested in when r is 15. So I'm going to plug in a 15 at this point. And dr dt, I think they told me was 6. So this is in inches, and this is in inches squared. No, what is it? It's just in inches per second. And the grand total is that dA dt is 30 times 6 is 18, is 180 pi square inches per second. They told me about one rate. They asked me about another rate. I found a relationship between the two variables without derivatives. Implicitly differentiate to get an equation relating the derivatives now, the rates, and then you plug in everything you know, solve for the one you don't. Now, this one happened to already be solved for the dA dt, so I could just plug them in here. Okay. One thing I want to point out in this one is that this was a function of r over here as well. This indicates to me that, if I had asked the question, how about when r is equal to 2? Right? Well, it would have been plugging a 2 in here, and I'd have gotten a substantially smaller answer. But that does make some sense to me too, because I'm thinking in terms of, if I think about every second, from the time it fills in, if you gain, what did I say, 6 inches, right? You gain 6 inches per second. So that first 6 inches, you gain that much area. For the next 6 inches, you gain, all this area. Well, that's substantially more area. That as the radius gets bigger, the area is going to be getting bigger faster. So dA dt is both related to dr dt and to r, because bigger r's are going to give you bigger amounts of area for the same change in the radius. Okay. Anyway, there is the expanding ripple problem. We will look at some others in subsequent videos here.